lectures. Today, in the 8th lecture, we will talk about functions of several variables and also partial derivatives, including the chain rule. Let us start with the definition of an n-variable function. For this, if you look at the notes, this definition is very similar to the definition of one-variable function. The only difference is related with the domain set. Domain set is a subset of the real numbers or n-dimensional Euclidean space Rn, and the variables are x1, x2 to xn. Note that in this definition there are n plus 1 variables, including w, x sub 1, x sub 2 to x sub n. But we call this function as a function of n variables because name comes from the number of independent variables, where independent variables of this function are x sub 1, x sub 2, blah blah, x sub n. Hence, we name the functions depending on the number of independent variables. And if we consider the domain of this function, the domain is also domain and range definitions are also given, very similar to the functions of one variables. For example, in this case, if we consider a function of two variables, means that we have two independent variables. Most of the time those independent variables will be represented by x and y. We have a function of two variables where x and y are independent variables, and y, z is the dependent variable. After those simple definitions related with the functions of n variables and two variables, we may pass through an example in which the domain of the function is wanted. If you look at the function f, it is the radical xy, that's the square root of x times y. But remember that the square root, inside the square root, there can be a non-negative expression. So it means that x times y should be larger than or equal to 0, which gives us the domain set that consists of the set of all xy, so that x times y is larger than or equal to 0. But this corresponds to first and third quadrants of the Cartesian coordinate system or the rectangular coordinate system, which is the shaded area in the diagram. Now, I want to give two more definitions related with the functions of two variables and three variables. Those are level curve and level surfaces, where most of the time for the words level surfaces, we will simply say surface. It is the function of three variable f of x, y, z, which equals to a constant. Those definitions most of the time are used in the solutions of some typical problems which are given in the lecture notes. Hence, after those definitions, I think we may pass through the limit definition of a function of two variables. But before that, it may be better for us to remember the epsilon delta definition for the limit of a function of single variable. Note that there is a very important inequality which is given here. Hence, before passing through the definition of limit for the function of two variables, we will have one more definition, which is the definition of open disk. But open disk means it is a circle with center at the point AB and radius r, excluding the boundary points, where this set is called an open disk. Now, if you go through the definition for the limit, epsilon delta definition for the limit of a function of two variables, this is very similar for the single variable functions. But if you note here that in the lines that I want to show here, f of xy minus L can be replaced by f of p minus L, which is very similar to the single variable function, and xy can be replaced by p, and ab can be replaced by p0. Then if you reread this definition, we can say that f of p minus L in absolute value is less than epsilon whenever absolute value of p minus p0 is less than delta. Then we write the limit in a very similar way. Hence, note that in this case, xy minus ab in absolute value less than delta is an open disk, which implies that absolute value of x minus a is less than delta and absolute value of y minus b is less than delta, where this property is so widely used in proving the existence of a limit by using the epsilon delta definition. As a continuation of those discussions, we can say that the properties of the limit of single variable function or one variable function are also true for the functions of 2 or 3 variables or n variables. And also in a similar way, sandwich theorem or the squeeze theorem can also be used for these types of functions that we will deal with. After those explanations about properties and the definition, we may go through 2 examples for the limits. And if we look for the solutions of those examples, for the first one, what we do first we put limit points, 1 for x and 0 for y, substituted in the example 1 in the function. Then we get the indeterminate form 0 over 0. And in this case, if we use the iterated limits, first x goes to 1, we take the limit of f as x goes to 1, and then the outer limit, that's y goes to 0. Then the second iterated limit is obtained by replacing by those limits. That's first we evaluate the limit of f as y goes to 0, and then the outer limit as x goes to 1. But those limits are 0, both are 0, since the functions f1y and fx0 are the 0 functions. So it tells us that if the limit exists, this limit should take the value 0. Now, if we go through the lines, punctured line, including the point 1, 0, where those lines are represented by the equation y equals to m times x minus 1. And if you put m times x minus 1 in the function for each y, we obtain m over x minus 1 plus 4m square. And if you take the limit of this function as x goes to 1, we get the result as 1 over 4m. And it means that in this case, this limit equal to 1 over 4m, but note that it depends on the limit value, depends on the values of m. If m takes different values, then the limit will take different values. But we have to remember that limit is unique, but in this case it is not unique because it changes by the different values of m. So we say that in this case this limit does not exist. Hence, if we go through the second example, in the second example, again for the limit points substituted in the function gives us indeterminate form 0 over 0, where for the iterated limits we get 0 in fact, but I think it is a very good exercise for you to show that the iterated limits of this function both are 0. But now to show that this limit is 0 by using the limit definition of the functions of 2 variables, epsilon delta definition, and remembering that x square is less than x square plus 5y square, we obtain that absolute value of f of xy minus 0 is less than 2 delta. And if we say that this is less than or equal to epsilon over 2, then we get a relation between delta and epsilon, which is given by the words that we found the delta, which is positive and less than or equal to epsilon, whenever the second line of order of inequality here holds. Hence, we can say that this limit is 0 in this case. But this problem can also be solved by using the squeeze theorem or the sandwich theorem, where in this case we say that absolute value of f of xy is larger than or equal to is larger than 0, strictly larger than 0, and less than or equal to 2 times absolute value of y. But if we take the limits of those terms, so the left limit and the right limit is 0, so by the squeeze theorem we have that absolute value of f, limit of absolute value of fxy is 0, which implies that limit of fxy is 0. But the most important thing that we should remember here is that if the limit value is 0, this implication that we use here holds. But if the limit takes any value which is different from 0, in this case, this implication does not hold. So I think we get some idea how to evaluate the limit of a function of two variables, or how to show whether the limit exists or does not exist. After this one, we may pass through the continuity definition of function of two variables at a point AB, where in this case, if limit of f as xy goes to AB is f of AB, then we say that this function is continuous in this case, where continuity on a set, in fact, can also be given in a very similar way. But to show whether a given function is continuous or not, we use a test which is called the continuity test, where in this case, this test says that a function f is continuous if the following three conditions hold, which are given here by the three items. The first one, f should be defined at the point. Second, limit should exist. The third, the limit value of function should be equal to the functional value of f at the point AB. In this case, using this continuity test, we may solve one example, where in the example it says that whether the function f is continuous or not at the point 0, 0. For the solution, to determine the continuity, we can use the continuity test, where in the first step of the continuity test, we should know whether f is defined at 0, 0, but it is already given that f0, 0 is 0. In the second item, we should determine whether the limit exists. In this case, we can say that the limit of this function can be evaluated by the methods that we did the discussion earlier. That is, we put 0, 0 for x and y, and we get the indeterminate form 0 over 0. And if we consider the iterated limits, the value again is 0. But if we use now the two-path test for non-existence of limit, we may look for the limit through the curve x equals cy square through the point 0, 0. In this case, the function f of cy square y gives the ratio c over c square plus 1. And if you take the limit of this result or the function as y goes to 0, the result is c over c square plus 1, which means again that this limit depends on the constant c, or in other words, we can say that this limit does not exist. Since the limit does not exist, the second item of the continuity test does not hold. Therefore, the function f is not continuous. So, if we want to get a very brief summary, what we mentioned here, we talk about the definition of functions of two variables, limits of the functions of two variables and the continuity. After all those, I think we remember that the derivative of a function can be discussed, but in this case, this derivative has a special name, which is called the partial derivatives. To understand partial derivatives better, it may be better for us to remember that the derivative of a function is given by this definition, but note that f has a derivative, or we say that f is differentiable if the limit of this Newton's quotient, which is called, or the difference quotient, exists. So this existence of limit tells us that the single variable function is differentiable or has a derivative at any point x in its domain. But if we consider the functions of two variables, in this case, certainly we have to consider the idea, or we can give an analog definition for the function, for the derivative of function. But in this case, the differentiation can be given for the different variables x and y in a different way, where in this case, this existence of this limit is called the partial derivative of f with respect to the variable x, and we write f sub x or del f over del x. So for the functions of single variables, we use df over dx, but for the partial derivatives, we use del f over del x. So d and del are used for different purposes in the differentiation. Hence, by this way, we give partial derivative definitions of f with respect to x and y, provided that these two limits on the right hand side exist. But remember that for the functions of single variable, we also give a geometrical interpretation for the meaning of derivative. In this case, we will give a very similar argument for the partial derivatives of function for f with respect to x and y. Now, if you consider a surface z equal to fxy, something like a part of an ellipsoid or a sphere that is given here in this diagram, if we intersect this surface by the plane y equal to b, this is the plane y equal to b through the line y equal to b, then the intersection curve p is obtained. And if we consider the tangent line L to this curve P at the point x equal to a, we say that L is the tangent line, so the slope of this tangent line is the partial derivative of f with respect to x at the point AB. In a similar way, the intersection of the plane x equal to a and the surface gives us the curve Q, where the slope of the tangent line S is the partial derivative of this function f with respect to y at the point AB on the surface. So those are very analog to the geometrical meaning for the derivative of a single variable function. If we want to say something about the higher order derivatives, in this case we will say that if the partial derivative of f with respect to x can be differentiated once more with respect to x, then we get d2f over dx2 and d2f over dy2, means that we differentiate f with respect to x 2 times, and it is either shown by f sub xx, f11, f12, but the upper part or superscript is in the parentheses, and those are the notations. But if we differentiate f first with respect to x and then the result is differentiated with respect to y, assuming that it exists, or the reversed order in the second line, in the last line, or we can say that those are called the mixed derivative of f with respect to the variables x and y. In general, those mixed derivatives are not the same, but they can be the same under some conditions where it is given by the mixed derivative theorem, where it says that if f sub x means partial derivative of f with respect to a, x with respect to y, mixed derivative fxy and fyx are defined through an open region containing AB, and if they are continuous at AB, then we can say now that those mixed derivatives are the same. Once more, I want to remind you that for the single variable functions, differentiability and have a derivative are the same. That is, we say f has a derivative or f is differentiable. The meanings are the same. But for the functions of two variables, existence of partial derivatives does not imply the differentiability of the function. In this case, this definition is given in a different form. I don't want to say more about this definition in this page, but I advise you to read it or recover more carefully once more, either using those summaries or the lecture notes given in the Moodle page. But this definition can also be given in a different form by using a limit idea, which are equivalent certainly. And in this case, we say that the function is differentiable if this limit exists. So if we go further related with the differentiation, that is, we need a chain rule similar to the single variable function. One of the theorem, which is one of the version of the chain rule in other words, is this theorem. That is, we have a function z which equal to f of xy, but x and y are the functions of t. Then either we can write this right hand side, but this right hand side is obtained by using the tree on the left hand side. Note that f has two variables, x and y, and x and y are functions of t. So if you want to consider the derivative of t with respect to z, it means that first we should differentiate f with respect to the first variable, or if you want to use this tree, f will be differentiated with respect to x, where this differentiation, this path, is called the differentiation. So we represent it by del f over del x, since f has two variables, x and y. Then we differentiate x with respect to t, but x is a function of single variable, so this differentiation is represented by dx over dt. If we want to get the second part, that's the differentiation with respect to t once more, we have to turn back to this page. Or in other words, if we want to approach from this point to another t, certainly we have to turn back to f, and then we have to differentiate f with respect to y, and then y with respect to t. Assume that, to understand better, those t represent an apple in a tree, and we want to collect all apples, and at the end we want to know how many t or how many apple do we have. So what we do, we start with f, we go through a branch of the tree, we approach x, and we from x we approach t by using another branch, such as we may say that this is a thin branch, and we collect one of the t, then we turn back f, and if we want to know the number of apple that we add in between these two branches, we should put a plus sign, then del f over del x times dx over dt plus del f over del y times dy over dt, which gives us the chain rule for the function which is defined in this form. For example, if we consider this case where z equals to 2 to the power xy plus arctangent x square minus y square, and x is a function of t, which is t cubed, and y is a function of t, that is radical t or square root of t. And if we want to find the partial derivative of z with respect to the variable t, z is a single variable function, So this differentiation is represented by dz over dt, that's here also, where in this case we differentiate z first with respect to x, that is, it is here, that is y times 2 to the power xy ln 2, plus derivative of arctangent x square minus y square with respect to x, which is this ratio, times the partial derivative of x with respect to t, which is 3t square. So if you note that, it is this 3. First we differentiate with respect to x and derivative of x with respect to t. So this is the derivative of f times derivative of x with respect to t. In a similar way, in this parenthesis we have the derivative of z with respect to y times derivative of y with respect to t. And if we substitute x and y in terms of t, so we get this result, where this is obtained by using the chain rule or the theorem that is obtained before this example. So this example or this theorem is used for the solution of that example. Another version of the chain rule is this one, that is, we have a function z which equal to f. F has two variables x and y, and x and y have two variables t and s. In this case, we can say that in this tree have two types of vegetables or fruits, t and s. Assume that, for example, this is an apple and this is an orange, or it can be another thing. At the end, we want to also know how many of them are collected. So we use this tree to write the equations on the right hand side, which is another version of the chain rule. In this case, if we want to use this version of the chain rule for the example, where in this case z is given here, x and y are the functions of s and t. This problem in this case, that is to find the partial derivatives of z with respect to s and t, we may use two different methods. We may write those definitions, where del z over del s can be evaluated in this way, and del z over del t can also be evaluated. If we go through another example, in this case we have a mixed derivative where we have a function f which will be differentiated with respect to y, and the result will be differentiated with respect to x. Now remember that the higher order derivatives of several variable function, so we can write it in this form. That is, first we will differentiate f with respect to y and then with respect to x. So we can say that in the first method, we may use the substitution, that is, in the function for each x we can put values. So we can substitute the functions u and y. We can say that u is x times e to the power y, that's the first variable of f, and also v is the function y square sine x, which is the second variable of the function. So in this case, f is a function of u and v. Then we can use the differentiation, partial derivative of f with respect to u times partial derivative of u with respect to y, similar to fv and vy. Then if we evaluate the differentiations of u and v with respect to y, we can write this result. Then we can redifferentiate this result with respect to x, which is given here. That is, in the second line, we use the product rule for the functions of differentiation. So it is the derivative of f sub u with respect to x, that's the first term, times the second, plus the first term times the derivative of second with respect to x, plus the same operation is true for the second part, and we have here. But the most important thing in those mixed derivatives, the differentiation of f sub u with respect to x and differentiation of f sub v with respect to x. Note that f sub u and f sub v are the functions of u and v, similar to the function f. So we can say that the differentiation of f sub u with respect to u is this parenthesis times x times e to the power y, and then we have f, then this derivative is e to the power y. Similar to this one, partial derivative of f sub v with respect to x is this parenthesis, and the rest is the continuation. Hence, we have to be very careful in these types of differentiation. Either we can use the substitution for the function, that is, we may substitute the functions or the new variables u for x times e to the power y, which is the first variable of f, and v for the second variable. Or we can use direct substitution without direct computation without substitution. In this case, we may name the variables as the first and the second variable. So we can say that partial derivative of f with respect to the first variable, which is f sub 1, times the derivative of first variable with respect to x plus partial derivative of f with respect to the second variable times the partial derivative of second variable with respect to y. So the differentiation is made with respect to y. But then we can reevaluate or redifferentiate this result with respect to x. So those are the notations that we put here. In this case, we can write the result f11, f12 in terms of the partial derivatives of f with respect to the first or the second variable. Most of the time, this is more simpler than the first one, but both are true and equivalent. So we can use any of these two for the computations. Hence, this completes the discussion or the summary for this lecture. So, we hope you will enjoy your classes. Goodbye.